Welcome to my channel Phi Concepts CHM. This is third part of the series of Introduction to Optical Fiber, where we will see about the propagation of light through optical fiber and about the acceptance angle. Propagation of light through optical fiber. This figure represents an optical fiber with a transmission of light based on the principle of total internal reflection. We can see this part, the white part that you can see, this is the core having a refractive index N1 and it is covered by the cladding having a refractive index N2. This is the axis of the optical fiber. When light is incident from one end of the fiber at some small angle, it propagates through the fiber without any refraction, that is, it is not coming outside into the cladding. So it will suffer total internal reflection at point A, B and C. So at these points no refraction will occur. This condition is fulfilled if the angle at which the ray is incident on the fiber is greater than the critical angle. The ray suffers repeated TIR. This is because of the cylindrical symmetry of the fiber, even if the fiber is bent. The light beam finally emerges out at the other end of the fiber with a fairly high intensity. We will denote phi as the angle of incidence of the ray at the interface of core cladding, and phi c is the critical angle of the same interface. If we consider the core and the cladding interface, here the angle of incidence is this theta r. This is the incident ray. This is the incident ray when you are considering the interface of the core and the cladding. So we will write down the Snell's law which we had seen in the first video of this series. We'll write it down, the formula sin phi c is equal to n2 upon n1. So we can write down the critical angle phi c by rearranging this formula. It will be sin inverse of n2 by n1. So if TIR has to occur, phi should be greater than phi c. In other words, the light ray is guided through the fiber without any losses of energy. We can call this optical fiber as an optical waveguide, which guides the light through this fiber. Next is the acceptance angle. We will consider the same optical fiber into which light is incident at one end. I had mentioned that this is the axis of the fiber. Here we will consider N1 as the refractive index of the core, N2 is the refractive index of the cladding, and the light is incident from the air, so we have to consider the refractive index of air, which we will denote as N0. Note that the refractive index of the cladding is less than that of the core. N2 is less than N1. So now we incident the light into the optical fiber at an angle theta I. So here we are considering the air core interface. You incident the light from the air into the core. So the light is entering at an angle theta I. When it enters into the core, it will be refracted at an angle theta r. So now this ray is acting as the incident ray for the core cladding interface. This is the second interface. This interface is the core cladding interface. So it is incident at an angle theta r, and it strikes the core cladding interface at an angle phi. TIR will occur only when this angle phi is greater than the critical angle phi c, since N2 is less than N1. That is the condition that is to be fulfilled for TIR to occur. That is, there should be a rarer medium and a denser medium. So as long as phi is greater than phi c, the critical angle, the light will stay within the fiber. That is, it will suffer total internal reflection. It will not come out. It will not be refracted outside into the cladding. Now, suppose we increase this angle theta I. So, if when you increase theta I, if theta is increased beyond a limit, then obviously this angle phi will change, and this phi will drop below the critical angle phi c, and then TIR will not occur. The ray will escape from the side walls of the flat fiber. That is, it will be refracted into the cladding. So largest value of theta I occurs when phi is equal to phi c. So we can say, see, suppose now here we are increasing the angle theta I. The light is incident not along this at this angle, but this angle theta I is increased. So the ray will get refracted at some other angle. This is the normal. Okay, it will be refracted at an angle which is below the critical angle, and hence TIR will not occur. It will be refracted outside. Here only the here the three mediums have been shown separately. This is air. In between you have the core, and here you have the cladding. So if you increase theta I, so in terms of like if this is the normal, okay, we are decreasing the angle of incidence here. Now we are decreasing the angle of incidence. The incident ray is bent towards a normal. Then the refracted ray will also be bending towards a normal. And it will be refracted out into the cladding. So the largest value of theta I will occur when phi is equal to phi c. So there is a maximum value of theta I for which the angle phi will be equal to the critical angle. It will be equal to the critical angle, and then TIR will occur. So we will consider the air core interface, that is the point of entry of the light into the fiber. We can write down the Snell's law for the air and the core interface. That is we have to consider this as the incident ray, and this is the refracted ray. So we'll write down sine theta I upon sine theta r is equal to n1 upon n0. If we rearrange this formula, we will write down sine theta I is equal to sine theta r is taken on the other side into n1 upon n0. Now, if you observe this diagram here, this is a right angle triangle. This is a normal. So this is right angle, and the other angles are theta r and phi. So theta r can be written as 90 minus phi. So we are writing down sine theta r as sine 90 minus phi, which is equal to cos phi. So in place of sine theta r here, in place of sine theta r, we replace it with cos phi. Now for an angle theta I max, the critical angle or phi will be equal to phi c. So we can write down this as sin theta I max is equal to cos phi c into n1 upon n0. Now we will consider the core cladding interface, which is a denser and rarer medium. Light is passing from the denser to the rarer medium. We can write down the formula which we had seen in the first video, that is sin phi c is equal to n2 by n1, where TIR is occurring. So now we will write down this sin phi c in this form, that is square root of 1 minus cos square phi c. You must be aware of this formula, which we get from sin square theta plus cos square theta is equal to 1. So we have replaced the sin phi c by square root of 1 minus cos square phi is equal to n2 by n1. Square this formula, you will get 1 minus cos square phi c is equal to n2 square upon n1 square. Then we can bring this term on this side and cos square phi c will go on the other side. So cos square phi c is equal to 1 minus n2 square upon n1 square. Cross multiply this, you will get n1 square minus n2 square upon n1 square. Then take the square root of this equation, you will get this. Square root of n1 square can be written as n1. So you have got cos phi c is equal to square root of n1 square minus n2 square upon n1. So we have got the value for cos phi c, which you can substitute in this formula that we have got earlier. Sin theta I max is equal to cos phi c into n1 upon n0. Substituting cos phi c here, you get square root of n1 square minus n2 square upon n1 into n1 upon n0. So sin theta I max can be written here, n1 will get cancelled out. You get square root of n1 square minus n2 square upon n0. Again for air, n0 can be taken as 1. So here we substitute 1. So you get sin theta I max is equal to square root of n1 square minus n2 square, from which you can get theta I max, that will be sin inverse of square root of n1 square minus n2 square. So theta I max, the formula for theta I max we have got that, which this theta I max is called as the acceptance angle of the fiber, which we can define as the maximum angle that a light ray can have relative to the axis of the fiber and propagate down the fiber. So this angle theta I, it should be less than theta I max. So only those rays that are incident on the face of the fiber making angles less than theta I max will undergo repeated TIRs and reach the other end of the fiber. So remember, when theta I is greater than this theta I max, there will be no TIR. So larger acceptance angles, if the acceptance angles are larger, that will make it easier to launch the light into the fiber. So in 3 dimensions, the light rays contained within the cone having a full angle 2 theta I max are accepted and transmitted along the fiber. So here we are considering it in the form of a cone with the full angle 2 theta. It will be twice of theta I max. So this cone is called as the acceptance cone. So the light which is entering inside through the acceptance cones, only those light rays will be traveling through the fibers. Anything outside the acceptance cone will not be propagating through the fiber. It will not reach the other end of the fiber. Thank you for watching this video.